The discovery of a magnificent large-scale image of the interstellar object 3I/Atlas, reported by Frank Niebling and Michael Buchner, marks a significant moment in modern astronomy. Captured on November 9, 2025, between 5:08 and 5:23 Universal Time, the image combines 5 separate exposures, each lasting 3 minutes, obtained with 2 powerful telescopes, the TC-140/f5 and the ASI 6200 mm. This careful stacking process reveals a stunningly detailed portrait of the interstellar visitor and provides an unprecedented glimpse into the dynamics of its jets and tail structures as it traverses the inner solar system. What makes this image so extraordinary is the visible complexity and size of the jets emanating from 3I/Atlas. The stacked image distinctly shows 2 anti-tail jets extending about 10 arc-minutes toward the Sun, coupled with a longer, more collimated jet stretching away from the Sun to an angular separation of roughly 30 arc-minutes. To put this into perspective, this distance is comparable to the apparent diameter of the Sun or the Moon when viewed from Earth, which immediately emphasizes the enormous spatial scale of these structures. At its present distance of 326 million kilometers from Earth, these angular measures translate to physical extents of about 0.95 million kilometers for the sunward anti-tail jets and roughly 2.85 million kilometers for the jet extending in the anti-solar direction. These measurements reveal structures that dwarf most previously observed cometary outflows and are approximately 3 orders of magnitude larger than the glowing halo around 3I/Atlas that the Hubble Space Telescope captured on July 21, 2025. That earlier observation had already suggested significant activity, but this latest composite image shows that 3I/Atlas has evolved dramatically, now manifesting an expansive and dynamic system of jets that rival or surpass even the largest known natural cometary tails. The presence of multiple distinct jets indicates an intricate and potentially volatile internal structure within 3I/Atlas. In ordinary comets, jets form when sunlight warms localized patches of volatile materials on the surface, causing sublimation and the ejection of gas and dust into space. However, 3I/Atlas, being an interstellar object rather than a native comet of our solar system, may possess unique compositions or structural features that lead to far more energetic or sustained outgassing processes. The fact that these jets are not only extensive, but also sharply collimated implies strong internal sources of pressure and possibly magnetic interactions or rotational modulation influencing their geometry. The simultaneous appearance of anti-tail jets directed toward the Sun and a major tail jet extending away suggests that 3I/Atlas is actively shedding material in multiple directions, a phenomenon rarely observed in such detail for an interstellar visitor. This discovery is particularly significant because 3I/Atlas is still months away from its closest approach to Earth, scheduled for December 19, 2025. At that time, the object will pass within about 269 million kilometers of our planet. Although this might sound relatively near in cosmic terms, it is still roughly 100 times larger than the full spatial extent of the jet structures seen in the current image. This means that despite the tremendous beauty and size of its jets, the object remains far beyond the reach of direct physical sampling by Earth-based spacecraft. Even particle probes aboard satellites orbiting Earth will be unable to intercept or capture any of the ejected material. The same limitation applies to deep space missions currently operating in the outer solar system. For instance, NASA's Juno spacecraft, which orbits Jupiter, will have its closest approach to 3I/Atlas on March 16, 2026, at a distance of approximately 53 million kilometers. While this is far closer than Earth's encounter distance, it is still about an order of magnitude larger than the scale of the current jet system. As a result, Juno's particle detectors, though exquisitely sensitive, will not be able to directly measure any dust or gas expelled from the interstellar object. Similarly, the European Space Agency's JUICE spacecraft, now en route to Jupiter, is about 64 million kilometers away from 3I/Atlas and is also too distant to detect its emissions or interact with the jets. This reinforces that 3I/Atlas will remain a primarily observational target, with telescopic imaging and spectral analysis providing the only feasible means of studying its physical characteristics and activity in the near future. In natural comets originating within our solar system, the velocity of material outflowing from the nucleus is typically modest, often around 0.4 kilometers per second, comparable to the local sound speed of gas at distances similar to that of 3I/Atlas from the Sun. If we assume that 3I/Atlas exhibits similar dynamics, the enormous lengths of its jets imply prolonged and continuous ejection periods. For instance, to produce the observed tail that extends several million kilometers, material must have been expelled for at least 3 months at those speeds. The shorter anti-tail jets, reaching up to 1 million kilometers, correspond to ejection durations of roughly 1 month. This consistency in timing strongly suggests that 3I/Atlas has been steadily active for a significant period, possibly since mid-2025 or earlier, maintaining powerful outgassing despite its increasing distance from the Sun. The behavior of the anti-tail jets offers particularly intriguing clues about the physical properties of the ejected material. Typically, a comet's anti-tail appears when particles emitted toward the Sun are pushed away by solar radiation pressure and the solar wind, forming an apparent extension that points sunward from the observer's perspective. However, the fact that these anti-tail jets from 3I/Atlas are halted only at a distance of about 1 million kilometers suggests that their internal ram pressure, arising from the mass and velocity of the outflowing particles, exceeds that of the opposing solar wind all the way out to that range. Given that the solar wind moves at about 400 kilometers per second, roughly 1,000 times faster than the outflowing gas from a comet, the solar wind's pressure should normally dominate completely. Yet the continued existence of these strong anti-tail features implies that the particle density within the jets is remarkably high. Since ram pressure scales with the square of velocity, compensating for the solar wind's much greater speed requires an enormous mass density in the cometary outflow, on the order of 1 million times that of the solar wind itself. This means that near the extremities of the anti-tail, the particle density must reach a few proton masses per cubic centimeter. Using these parameters, the total mass flux through the outermost regions of the anti-tail can be estimated at about 2 million kilograms per second per million kilometers square. If we sum this flux over an effective cross-sectional area of roughly 10 million square kilometers, the total mass loss rate from 3I/Atlas reaches an astonishing 50 billion tons per month. Such an immense rate of material ejection places 3I/Atlas among the most active comet-like bodies ever observed. Interestingly, this value is comparable to the estimated minimum total mass of the object itself, around 33 billion tons, derived from the absence of noticeable non-gravitational acceleration in its orbital motion during the months before October 2025. Normally, comets lose only a tiny fraction of their total mass through outgassing, but in this case, 3I/Atlas appears to be losing mass on a scale comparable to its entire nucleus, suggesting either extreme surface activity or the fragmentation of its structure. If the object were composed of loosely bound ices and dust, such vigorous mass loss could rapidly reshape its surface or even lead to partial disintegration, a fate that many comets face after close solar passages. Assuming that 3I/Atlas has a bulk density of about 0.5 grams per cubic centimeter, a typical value for porous, icy cometary nuclei, these mass estimates imply a minimum diameter of more than 5 kilometers. This size makes 3I/Atlas significantly larger than many comets observed in the solar system, and if much of its nucleus survived its perihelion passage, its full diameter could be as large as 10 kilometers or more. For comparison, Comet Halley measures about 11 kilometers across, while Comet 67P/Churyumov-Gerasimenko, visited by ESA's Rosetta spacecraft, is roughly 4 kilometers in diameter. Therefore, 3I/Atlas stands among the more massive and enduring cometary bodies known, especially considering that it has survived a journey from another star system into the harsh environment of our Sun's gravitational field. The implications of these observations extend well beyond the immediate data. Because 3I/Atlas is only the third confirmed interstellar object to pass through our solar system, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. It provides a unique opportunity to study the composition and behavior of material formed in another stellar nursery. While 2I/Borisov appeared relatively similar to typical solar system comets, 1I/Oumuamua displayed anomalous acceleration and an unusual shape, sparking debates about whether it was natural or artificial. 3I/Atlas, by contrast, exhibits distinctly cometary characteristics, including large jets, strong mass loss, and observable dust tails, though the immense scale and density of its outflows push the limits of what we have previously considered normal. Future observations from the Hubble Space Telescope and the James Webb Space Telescope will likely reveal further details about the composition and structure of the jets and the nucleus. Spectroscopic studies could detect specific molecular signatures, such as water, carbon monoxide, or more exotic ices, that will shed light on the environment in which 3I/Atlas formed. Because it remains at a considerable distance from the Sun, even at its closest approach, these telescopes can observe it without the interference caused by excessive solar glare or rapid heating. As it continues to move through the solar system, the evolution of its jets and overall brightness will also help astronomers understand how interstellar comets respond to prolonged solar irradiation after potentially spending millions of years in deep interstellar space. In summary, the November 2025 image of 3I/Atlas represents a milestone in the observation of interstellar objects. The extraordinary scale of its jets, the persistence of its anti-tail structures against the solar wind, and the massive outflow rates all point toward an unusually active and possibly very large nucleus. Whether this object behaves like an overactive comet or exhibits properties unique to interstellar bodies remains an open question, but a study will undoubtedly enhance our understanding of cometary physics, interstellar chemistry, and the diversity of small bodies that travel between stars. For now, 3I/Atlas continues its silent journey through the solar system, trailing vast, ghostly plumes that stretch millions of kilometers across space. A vivid reminder that even the smallest visitors from distant worlds can illuminate the grand mechanics of the universe in breathtaking detail.